Hi, now I'm going to let you know regarding a very important topic called simulation. For that, we'll open a part which is already made. So, we'll open it and we'll use our sweep part for this simulation. And for this simulation, we need to go to evaluate, and in evaluate you will find many options, out of which this is the simulation express analysis wizard. So left click on this part and the wizard opens. Now since this is very important, we need to know why it is very important. First of all, I will let you know what a simulation is. Simulation is like if there is a part and some loads are applied on the part, so in real life what happens actually with the part, it gives some kind of results. So to obtain those results, and if we already know whether the part is going to break once the part is made, then there is no use of such designs. So to validate such designs, we need to use the simulations and check how the part operates in the real life world scenario. So once you open the simulation wizard, you will see a welcome screen on the right hand side. In the screen you will find an option start over, so left click start over and yes, and then go to next. Now we are performing the simulation basic for 3 options. The first option is, this is a part which I have made, and in this part I want to check the factor of safety. So this is one thing. The second thing for checking the simulation is the stress concentration. Where could be the stress concentration on this part? And the third thing is the deformation, or you can also let us know the displacement. Where could be the maximum displacement and the deformation on the part? So these things will be explained. So once you open this thing, you will see on the right hand side there are few things: fixtures, loads, material, run, results, optimize. And on the left hand side you will see the sweep command by which the part was made, and the fixtures and external loads. Now we need to apply some fixture. What is a fixture? If a fixture is applied to a face, then that face doesn't move, at least to some extent, under application of a load. And fixtures are really necessary. So we'll see some of the examples of fixtures as you can see in this animation. So the fixtures are the green colored things on the top and side. So the part you can see is moving, but the fixtures are not moving. Second, these are the fixed holes. In second, we'll see fixed versus supported. Go here, just go here, and you will. Yeah. So about the pressure, what's a pressure? The formula for pressure is P is equal to F by A. Pressure is equal to force upon area, and force is calculated in newtons and area in meter square. This is the general engineering which I am letting you know. So pressure is how much force is applied on a meter square area. Now we'll come down and we'll see what is a force, how to calculate force. Force is generally weight. Weight is always in kg, and the formula for force is m into a g, is mass into gravitational force. So it's let it be any mass, and then 9.81 is the gravitational force. So this is force. And pressure is equal to force upon area. So now going back to our Solidworks, and then what kind of load I want to apply. Let's say I just want to apply normal force. normal force. Now I'm holding my hands on this handle, so definitely I'm pushing it downwards. So I'm going to apply some force over here and some force over here. Okay, now how much this force could be, I don't know. I really don't know. Let's say I'm applying it with hands, then it could be 10 newtons. But let's say I'm applying the force with some kind of machine, so it is definitely not 10. I will apply some higher amount of values, which can be say 10,000 or 50,000. Yes, I wanted 50,000. Yeah, then I'll make it okay. So green color is a fixture and the pink colors are the loads, which is a force. Make it okay. This is in Newton. You can also change the unit to English IPS, but no, I will use it. It's a selected direction. Look, it shows which direction you want to apply force, but say I want to apply it the normal ones. Yeah, you also reverse the direction. This goes up. It's pulling action, some kind of pulling action. Well, you may need this in some of the parts, but no, here in this case I want to apply force. You can also apply force over here somewhere depending on your case. Make it okay. This is okay now I don't want to apply pressure anymore, and if I want to edit a force again, I will left click here and then I can see 50,000 newtons. I can also change the force, but for now I don't want to change the force, so I'll make it back and then I'll make it next. Now material, what kind of material I'm going to use for this part. I have not specified any material. As you can see on the top hand side, material not specified. I can also specify material from here and from here, as in this case. So left click, choose material. Now say what kind of material I want to use. Alloy steel. Let's use alloy steel, that's okay, and apply. Okay, close. Look, it shows the Young's modulus and the yield strength. So I have applied the material alloy steel. Now again make it next. Now do you want to change the settings? No, directly go to run simulations and we'll run the simulation, the 4th point. Let's see what happens now. This is amazing. So here, okay, run. So it will calculate some, it will apply some meshing areas, and then it will show you how the simulations is going to work. Look, can you see how the part is moving? This is the fixture. So this fixture is not moving, but here look how the orange colored line is the original line, and how the deformation occurs, how the displacement occurs. So force is applied from the top, so it goes down. Generally this is exaggerated to show you how your part works. So now if you are satisfied with how actually the part deforms, is this proper or not? Yes. Does the part deform as you expected? Yes, somehow it deforms in this way only. Yes, I'm satisfied with this. So yes, then you need to continue. So we'll stop the animation first and then we'll continue. Or if you are not satisfied, then go to load and fixtures, so you can change your the face of the load. But now I'm satisfied, so yes, continue. Now it's done. You can see the results. 1 minus stress and the displacement. First we'll see this one, 1 minus stress. Look, now here it shows the yield strength. Yield strength is 620.422. It shows this red arrow, which means maximum in our part it goes to 6 20.422 Newton per millimeter square. So this is the value how the stresses are distributed. You can also check the color codes. The blue color one is the dark blue color is the this one which is having the lowest stress. Okay, and then the stress increases. Oh yeah, in this case you can play the animation also. Play animation. Look, now can you see this remains blue, so there are no stresses in this area. And then how the color changes, the color changes means if it comes green means more amount of stress accumulates on the edges over here, and maximum red color stress is over here. So this is about the stresses, how under the action of stresses this is moving, the part is bending. Now we'll stop the animation and we can go to displacement. Show displacement. Look, now we'll see where the maximum amount of displacement occurs. Look, this is blue, this is blue because it is not moving. Yeah, and this is red over here. The maximum red which I can see is over here. So this is the maximum area in which displacement occurs. Like, again I will play the animation for you. Yeah, look, this is blue, so it is having no displacement at all, but this thing is having the maximum displacement over here in the part. How it looks when it undergoes the maximum deflection, so which is 1.45 millimeters almost. We'll stop the animation over here, and here you can see what is the factor of safety in the part. Look, based on the specified parameters, the lowest factor of safety found in your design is 0.832, which is very less. Why? Because generally factor of safety is like keeping it 1. If it is more than 1, then yes, your part is safe. If it is less than 1, then definitely your part might break because it is not safe. And you know, if it is more than 1, like 2, 3, 4, then it's very safe. So here my factor of safety is not safe. So what I can do is I need to change some of my parameters to make this factor of safety 1 or more than 1. Definitely it is close to 1, but still I need to change some of the parameters for my design. What this thing is, show where the factor of safety is below 1. It is below 1. It shows me, look, it is over here in this area. It is below 1. That's alright, but again we'll change some of the parameters. So for that thing, what I need to do is I'll play with the load. What kind of force have we used is edit definition. Right click and edit definition. It's 50,000. I'll use only 10,000. Make it okay. This is 10,000, and then I will make it next, and then again materials is the same, and then I will run the simulation. Left click. Now again it will mesh. So there are many factors like, yes, now see, factor of safety is 4.61. so this changes with the loads. The more the load, the less safe your design is. The less I have changed the load, the factor of safety increases. So now the part is very safe, 4 times safe than what I need. And it also depends on what kind of mesh you are using in the system. Yeah, what kind of mesh. It's a solid mesh, volume mesh, different mesh. I will show you later on about the mesh. But yes, now I've done viewing the results. This is good for me. I can also play animation. Oh, the animation not available. That's okay. Now about the stresses. Again this thing. Yes, now animation is available. This is how the part moves with 10,000 Newton force. Okay, now stop the animation and then go down. Done viewing the results. Now there are two reports. It goes back to the original state along with fixtures and loads, and generate report and generate edrawings file. So what's in report? Report includes a Word file which includes many things. I will show you. And what's edrawings file? But first, with the report, left click and it generates a report. Now in this report, this is an editable report in which it gives a good format. In that format I need to write something. So the description, what kind of analysis is this? So you can write this is what you call is my sweep part. So sweep part load analysis. This is my load analysis, and load analysis, factor of safety analysis, and deformation analysis. Yeah, that's it. And what are the conclusions? The conclusions can be anything. My aim is to reduce the weight with factor of safety equal to what it says 1 or more. You know, factor of safety should be greater than or equal to 1 or more. With the part should reduce the weight, or you can say not to reduce the weight, optimize the weight. This is my conclusion. And you can see, like, name of the company can be anything, DB Private Limited. Okay, and then you can fill some of the details over here, and then you can generate a report over here. The document name will generate a report. Yes, I will overwrite the report I already generated, and then a report will be generated. Look how it will generate the report. What are the different things in the report? It's a kind of perfect report which includes a bill of materials. It contains the images, the file names, the properties of the different parts, and what kind of displacement and stress distribution in the part. So it tells you step by step, simultaneously, everything. So this is the most interesting thing. I'll tell you. Look, now this is the report. Simulation of sweep. The table of contents and tells you about the description which we have mentioned and how the part looks. It tells you about the assumptions, the model information, the properties, loads which we have applied, the material properties which we have applied, about the mesh which I was going to tell you, the results and conclusion. Come down, we'll see some of the assumptions. The assumptions are like, this thing is fixed, we have assumed the fixtures and what kind of load are being applied. Well, let's again come down, and then we'll see the solid body and the volumetric properties of the part, like what's the mass, volume, density, and the weight. Alright, and we have specified the material, so definitely we have its density, and then because we have the density and volume, we will have the weight. We'll come down and we'll see alloy steel is a material which we selected, and the yield and tensile stress was already mentioned. Now it says about the fixture where it is being applied, and also it tells us about the force. and how much force is applied is 10,000, as we know. Now the mesh, the solid mesh is being used, and the mesher is the standard one, so it tells you about the tolerance in the mesh, and the mesh quality is good. And some more points related to the mesh, like the nodes, the elements, the aspect ratio, etc. And then how the mesh looks. Look, this is how the mesh looks. The triangulated areas, the triangulated section which are joined by the edges. And then about the stress, everything about the stress. Where's the minimum amount of the stress in the part, and where's the maximum amount of stress in the part. So here you can see the maximum amount, which is the red color, and the blue color is the minimum. And now the displacement is totally opposite. Displacement maximum is here and minimum is here. So this was about the displacement. And now the deform shape, how the part will look. Generally it won't change more because the displacement is less. And then the factor of safety, that tells us about factor of safety. And see how safe the part is. This part is saved. About our conclusions. So this was about the report. Now about e-drawings. Now why we need e-drawings? So the thing is, why we need an e-drawings file. You know, when you're making any part, you're working in a company, and you work for some other customers, and the customers says that okay, make my part. And if it's a long project for 5 days, 6 days, 10 days, and you want to update the customer regarding the status of the part you have made, then in this case what you do is you make an e-drawings file, because the software SolidWorks, if at all, is not installed in customer's PC, then it's alright. You can make an e-drawings file and show them and update them regarding the status of the part which is being made, and then carry on. So you don't need a SolidWorks software to be installed to view an e-drawings file, but definitely you can view your part in 3D along with the load, fixtures, stresses, everything. So we'll generate an e-drawings files in this case. Left click, and it shows where you want to save. I want to save over. I will overwrite, save, yes. Now this will open a wizard of e-drawings file. Register later, yeah. And this is where we can see, look how the part looks over here. We'll zoom out for you, and this particular, here it shows the stress distribution, and this is zoom area. If I want to zoom this area, left click, hold, drag, and zoom, and see how the stresses are, and then zoom to fit. And this is zoom with mouse button, scroll button you can use. This is rotate, left click and then rotate. This is pan, look, left click, and this pans, this perspective. And then what I will do is, this is animation, we'll play the animation. Look how it plays the animation, and in what sequence it plays the animation. So I'll tell you the sequence. We'll stop it first. It has generated the stress, the distribution, the displacement. Okay, see how deformation looks. Not much deformation in the part. And the factor of safety, this is blue in color. Here you can see the mesh, stress distribution, and then we can click mesh. What kind of mesh is used? Look, triangulated mesh, solid mesh. But this looks great, yeah. And this is the title, choose the title, what is the name and the plot type, and there are a few options. We'll close it. This is the legend which shows the distribution stripped. Okay, and then we'll go to this option. Look, this option is the animation option. Like, it starts from isometric view, then it goes to front view, then right view, then go down to back view, top view, left view, and bottom view. But I want initially to start it from, I want top to be upwards, up, up. I want bottom not over here but up, up, then front, and then I want back, so make it back, then I want left, and then right. So in this sequence animation is going to play now. So starting from the isometric view, look, play. This is the isometric view, then it goes to the top view, now it goes to the bottom view, now it goes to the front view, now back view, now left view, and finally it goes to the right view, and then again to isometric view. So this is how it moves. And then if you go down, you'll find the markup commands. In markup commands, these are some of the inactive commands over here because it's not a full version. But in markup command, what happens is, we'll stop this thing. It's not stopping, it can stop from here. What happens is, this is annotations, text along with the clouds. Like if I want to write here it's a maximum displacement, or here is the maximum stress, or here need to change the thickness. If you want to show it to your customers, then definitely this is very useful, so they will understand in a better way. So similarly, these are other functions which are inactive. And again, if you go down a little bit, it shows your part in section, how your part looks in section, if it's a hollow part or a solid part. And there are some of the stamp features, like whether this part is approved or not approved. It shows some of the stamps. So this was about edrawings, and we'll close this, or else we'll keep it open, and we'll open the Solidworks, and then we'll go to next directly. In next, what you can see is, I will minimize it. Yes, now here it shows, would you like to optimize your model, yes or no? It's a very good question and very important question. Why this is important? Because if you want to save your material to a large amount of extent, along with the application of the normal force which you were applying, so why waste more material and more cost and more time in making such things? So this is very important and very necessary. Nowadays people and engineers do use this option, because anybody can design on the earlier options, but the optimal part or the optimum dimensions in the part are really necessary for a successful engineer to work on. So we'll make it next. When you make it next, you will see some of the options, you will see some of the annotations which are being made while designing the part. And here what you want to reduce is, what I can say is, this was 60, this is 95, so I will reduce this 95, because I think I don't need this 95, I need something else which is less than 95. So I will select this 95, left click, and it shows some D2 sketch in the part. I will do it OK, and then here is 95 one thing, yes, and it shows the minimum and maximum. So what I can say is, I want it lesser value, so here I will make it 95, because maximum should be 95 but minimum should be anything, but maximum should be 95. And I will apply some of the constraints over here. Left click, factor of safety. So our factor of safety was 4, so it's too much. It's too much. So I don't want factor of safety to be 4. It's okay if the factor of safety is 2. It's okay. So yes, I would decrease the factor of safety, and then I also want the thickness to be reduced, but along with the application of 10,000 Newton force. So let's run this optimization. Left click, run. So now it is running, and there are 5 scenarios on which it runs. It calculates automatically, and then it shows the optimum results over here after this is finished. And let's see whether our optimization is possible or not, first thing. And if it's possible, then how much it is possible. Yes, if it shows the optimum values, then definitely it is possible. Now we'll see the results. These are the results, the initial results and the optimal. Initially, our part, this D2 sketch 1, which was the thickness over here, was 95, but now in optimization it is reduced to 62. So this is a good thing, good sign. Now the factor of safety was 4, now it is 2, because we have selected minimum we need 2. And then the mass was 34 kg for this part, for the alloy steel, but now it is reduced to 22. Look, this is a great thing, a great achievement we can say we have shared. But still, here what happens is the factor of safety is 2 and the mass is 22. This is a very good sign. Again, I think we can still reduce, we can still go down, and we can still reduce the thickness. But in this case, what I can say is, what if I increase the load, because the load is constant in both the cases. Do I need to do anything with the factor of safety or the thickness if I increase the load? Let's see what happens if I increase the load. Now this has changed. This is the initial. Look how a part used to look initially, and look how it looks. Lesser, more, less. So these are the optimal regions. Now this will work on these optimal regions. Now this is no more 95, this is 65. Okay, but now I want to apply the load. I'll change it, go to loads, and I will click here so it goes down. I will click here somewhere, yeah, it goes down. Then the load which I applied is edit definition, and 10,000 I will use it 15,000. Okay, right click and zoom out, and next, then again next, and then we'll again run the simulation, because running the simulation is very much necessary for the part to to take the new load, which is, look, force to value 15,000. Now again we can generate reports and edrawings file, but in this case I will check the optimum values first, so I'll make it next. Look, it shows the initial value was 4, but now it's 2 for the factor of safety. Yeah. And then we'll see, run the optimization. We'll see next. So we need to understand whether it is taking 15,000 load or not. We'll run the optimization. Again it is running the optimization on these values, and let's see this time what happens. It has not shown the results. Make it next, back. So initially, now after the optimization was calculated, the factor has safety become 1.22 and mass is 22, but the thickness is the constant. Look, yes, so optimization is done now. I tell you, previously factor of safety was 4 and in second time it was 2. So when again the optimization was made to run, initially it was 2 and then it became 1. Mass was also more and now it's less, but the thickness is still the same. So we had done 3 cases. First and in second case the load was same, but these values were changing, these 3 values. In second and third case, this is the last case, third one case. In second and third case, what we did is, the first line is same, 62, the thickness is same, but factor of safety is reducing and loads are increasing. So when loads increase, factor of safety decreases. And if you want to decrease the thickness, if you are decreasing the thickness, the factor of safety increases. So these are our results. Such results we can write in the conclusion tab and then produce it. Also the mass has a great effect on it. Okay, back. So this thing was our simulation express analysis wizard. So such type of simulations can be done with different amount of parts to check the real life scenario. Thank you.